A 58-gram tennis ball travels through the air with a horizontal velocity with a magnitude of 18 meters per second. It is then hit by a tennis racket, and after 0.150 seconds of contact with it, the ball is going at 34 meters per second in the opposite direction. What was the average force applied to the tennis ball by the racket? So, situation we're talking about here is like maybe here's this ball, right? Let's say it's flying to the left here at some speed. This is maybe that 18 meters per second. And then at some point here, thwack, the tennis racket hits the ball, and now it's going out at a much larger speed of 34 meters per second. So that's kind of my sketch of the situation. And in that sense, I can look at this and say there's clearly change happening. There's an initial state, final state for the tennis ball. The concept I think I'd like to apply, though, to this is the impulse momentum theorem, stating that impulse is equal to change in momentum. You might say, well, okay, looking at that formula, like, how do you answer the question with that? There's no average force in there, is there? Well, but remember, the impulse is equal to the average force times amount of time. And so I can put that in for impulse here and set that equal to the change in momentum. So maybe what I could do is, if I could figure out what the change in momentum is, I could figure out the average force. And, I've kept all the vector symbols on here. In this class, we're not getting too deep into the notation of vector mathematics. So usually we're using pictures, and at some point we use our intuition to figure out what we're supposed to do. Let me start out, though, with the change in momentum, although maybe instead of writing it as a vector, I'm just going to look at the one-dimensional change in the momentum. Maybe I could even assume that we have some like standard x, y coordinate system, and in that sense I've drawn this with initial speed or velocity in the negative x direction to the left, right? Negative x direction, and then final to the right. And so thinking about change in momentum as being p final minus p initial, and then that being the mass of the tennis ball times the final velocity minus the mass times the initial velocity. Okay, that's kind of what I'm doing here. But, and this is the part where I got to be a little bit careful here, is direction matters, right? In that sense, maybe I could have also labeled it and say, really, I'm talking about x components. So they can be negative, in other words. And in that sense, like if I say, okay, the mass is 58 grams, I'm actually going to turn that into 0.058 kilograms, because that's the base unit. That's I think I'd like to work in that base unit, because since I'm going to find a force eventually, if I want it to be in newtons, it might be helpful if I work in base units right now. But that final velocity is clearly a positive 34 meters per second. And then I'd say minus a 0.058. But here is the part where there'd be real potential for mistake, is we have to recognize the initial velocity was in a negative direction in the kind of implied standard coordinate system that I'm using here. So for that one, let me open a set of parentheses here. I'm kind of running a little low on space, but I think I can fit this in here and put the minus 18 meters per second. Barely have space to close that parenthesis there. So that's something that I can then put into my calculator and get a number for. Maybe I could actually simplify to just 0.058 times the sum of 18 and 34, since those minus signs cancel and you can kind of undistribute the 0.058. But whether you do or do not do that, the number that I got for this was 3.016, and this is unrounded right now. This should be in kilograms meters per second, right? But looking at this equation right here, I think it makes sense that the average force I'm trying to calculate, if I divided both sides by the time delta t, I'd be looking at basically the ratio of this change in momentum to this. In that sense, when I look at this question, could we have just started maybe with Newton's second law in this form, is not even have used impulse? I guess we could have, right? Maybe. But we're doing impulse, so we did it that way. Anyways, if you take 3.016 and divide, let me write that in here, 3.016 kilogram meters per second, and divide that by the time that's given there, that's kind of the contact time. So that really is the time during which this interaction is taking place, right? So that's the appropriate time. That's when the momentum is changing, right? So hence the appropriate time to put in here. And my calculator says that's like 20.10666, etc. But I think given the way everything is looking here, maybe it's okay to just say 20.1. What units should I put? Well, this is a force. I might expect to get newtons, right? And maybe you can see that in here. It's kilogram meters per second per second. That's really going to be the same as kilogram meters per second squared, which is like a mass times an acceleration, which is kind of what the Newton was originally defined based upon. So I really think that is a Newton there. So there it is, 20.1 newtons.